So Gauss's law is all about symmetry. Let's see what I mean. I have here the simplest charge configuration imaginable, right? A point charge. What Gauss realized is that, well, one thing is that this charge will emanate an electric field outwards from it, right? It'll go from positive charge into negative charge. The second thing Gauss realized is that if he were to hypothetically surround this charge with some closed surface, right, of whatever type or shape that he chose, then he could, in theory, add up the surface of that object to help estimate, well, the electric field coming from the charge inside of it, right? Let's take a closer look. What we want to do is come up with a surface, right, or a shape, such that the electric field is an even or constant magnitude at all points from this charge. So, in other words, if we were to surround it with, oh gosh darn it, if we were to surround it with, say, a cylinder, right, a hypothetical Gaussian cylinder, then the electric field that's coming from this plus charge will poke through this cylinder at various points, like that, right? Like that, it'll even go like that. It might even go down, right? All space, but I've only drawn a couple here. So this electric field will poke through at certain spots. So let's see, on the right side, remember that area vector is perpendicular to the surface at that point. So that dA is actually directly to the right. We can write that like such. It's in the normal direction. It's poking through this top section and going straight up, right? dA, and that's E. Same thing over here. dA is upwards. On the left, very similar to what I drew first. Okay, dA is outwards. And on the bottom, dA is down. So why isn't this one a good choice? Why isn't a cylinder, in this case, a good choice? Well, let's take a look at the distance in between the charge and where the electric field pokes through this surface. So for this one, that distance is, well, that far, right? In other words, R. The electric field has some magnitude at this point that's dependent upon the charge, yes, and the distance to that location. Comparing that value to the electric field right here, that's a little bit further away. The charge is still the same, so thus the electric field magnitude at this point will be slightly less than over here. This distance, I guess as I've drawn, happens to be the same as this one, so these two magnitudes will be the same. However, they will not be the same as what it was over here, right? Same thing for this location over here, right? This distance looks to be just a smidge longer than this distance, right? So the electric field magnitude at this position will be different from both of these up top and the one on the right side, okay? So that's it, right? That's why this cylinder is a bad choice. The electric field at all points that it penetrates the surface is not the same. We want to choose a surface where it is the same. So a cylinder is a bad choice. Let's erase all that. Can you think of another shape of object, right? Another type of surface that can surround a positive Q charge, just one point particle, such that the surface is equal from the charge at all points, right? It's not a cone, right? It's not a box. Boxes are bad, Well, the only thing I can think of is a sphere. Right? I've drawn it close to centered. And so now the distance of that charge to the surface of this Gaussian sphere at all points are equal. Okay? And so that means when the electric field penetrates this surface, regardless of where it does, it's always the same strength. Right? Because this is a distance r away. This is a distance r away. This is a distance r away. You get the picture, right? That's a sphere, a Gaussian sphere of radius r with the charge q at the center. And so this dA is now in the exact same direction as the electric field. Same thing for on the right, right? That dA vector is now in the same direction as E. The same thing happens down here. Right? It happens for all points on this Gaussian sphere. The area vector always is normal to the surface at that point. And if you choose a sphere around a point particle, dA is in the same direction as E. And so this is a great choice of a Gaussian surface for a point particle, right? Again, because the magnitude of the electric field at the surface of this sphere is the same, and that's because the surface is the same distance from that charge at all points. So now let's take a look at another type of symmetry. What if you don't have a point particle, rather a different charge configuration? What if you have a line of charge? Right? Let's draw straight line. Well, let's see here. This has charge Q on it, right? Well, actually, let's write this as not necessarily Q, but a better way to write this is lambda, right? The charge density is the same or constant. So this is charge per unit length. What about now? Can we use a sphere now? Right? If we draw a sphere, even if that rod bisects it through the equator, take a little chunk of that rod, right? A little chunk dq, that will create its own electric field. Well, that creates a field there, and there, and there, and there. However, yes, those distances are the same, there, there, and there. But we have other dqs, say, over here, that are doing the same thing, right? And that's creating an electric field that way, and that way. And now, this distance is not the same as this distance, and is not the same as this distance, right? It's only equal for one dq, but that's not, well, the object we have. We want to find the electric field created by this entire rod. So a sphere is not a good choice for a line of charge. We need another Gaussian surface. There's our line again. Okay. So the surface that's equidistant from a line, well, is a cylinder now. Let's draw a Gaussian cylinder such that this line of charge is through the center. And the great thing about Gauss's law is that we don't have to have that Gaussian surface to be necessarily the entire length. You can, but you don't have to. Because now if we want to find the electric field, say this far away, it's the radius of that cylinder. What's the electric field at point P? we can do that, right? Because now every point on this Gaussian cylinder is the same distance away, right? Notice I didn't say that's a closed on the end. It's just an open cylinder. Okay, so if you think three-dimensionally, the points here, that's the same distance to the line as up here. Okay, same thing for in the background. That's the same distance as that. Okay, so a Gaussian cylinder centered on a line of charge is the appropriate choice for a line, right? And we have one other main one in chapter 23. We have a plane, right, or a plate. Right, so we have a flat plane or a sheet of charge. So for sheets, the charge density is sigma, charge per unit area, and that's constant here, okay? What type of surface, Gaussian surface, should we choose for a plate? Well, we can't do a sphere again. That's too tough to draw, but if you can picture kind of like a top hemisphere, right, on here, top hemisphere, and then it's right there. We're going to have all points different directions to that. Let me try that again. Right, all points will be different direction, or different distances, sorry, to that Gaussian surface. So a sphere is not good. A cone is even worse. A square is even worse, right? Now, we can use, let me draw this bigger. For a sheet, it's actually a cylinder again. Right? I guess on top I can do solid lines. There we go. So it's a cylinder on top, and on the bottom, it's the exact same. Okay. And now, this is important. For a plane or a sheet of charge, we have to have the height of this Gaussian cylinder to be the same. Why, might you ask? Well, think of the electric flux, right? This sheet of charge will create an electric field going out from it, right? Both up and down. That's both electric fields, okay? So in this Gaussian surface, which surface will that have a non-zero flux through? Will it be the sides, right, around here? No, it won't. It'll be the top and bottom, right? That's the area, or that's the surface of this Gaussian. It's called a pillbox in some textbooks. This Gaussian cylinder, if you will. Those are the sides that will have a non-zero flux, right? The top and the bottom, because that normal vector, that dA, is in the same direction as E. The dA for the sides, right, like that, and over there, what's the electric flux there? Well, E dot dA, right? Well, the angle in between E and either of these dAs is 90. And so if you take cosine of two vectors that are 90 degrees apart, you're going to get 0, right? So there is 0 flux out the sides. But you'll get maximum flux about the top and the bottom. And more specifically, or more importantly, they have to be the same height, because at this height of the top, you're trying to find the electric field magnitude, right? So that's a distance of h from the actual charge. Just like on the bottom, you are trying to find the same thing, the magnitude of the electric field at a distance h on the bottom. So they have to be the same distance, right? They have to be symmetric, in other words. I suppose you could do a box, right? You could do a rectangle. I know I mentioned a box was bad earlier. You could do that, right? I've just always used a cylinder. All of the books I've been using have used cylinders, but I guess a box could work too, okay? But choosing your type of Gaussian surface, choosing the symmetry, right, is very important, if not essential to these problems. That's the key to Gauss's law, is choosing the appropriate symmetry to simplify your math, right? Simplify your math.